Hi everyone. So in this video, I'm going to talk about angle. It is a very important concept. We use it a lot in physics. So I wanted to make a separate video on this so that we can discuss it in detail. This video is going to be mostly conceptual. I'm going to, discuss two very pressing questions. One is angle has dimension. It doesn't have dimension, but it has unit. Why is that? And the other question is, oftentimes when you see angle in an equation or expression, um, how do you know whether it is in degree or radian, right? So these are two very pressing questions that students often have. We will talk about that among other things. All right, so these are the things that I'm going to discuss in this video. What is angle? How to measure degree versus radian? Why is a full circle 360 degrees and not any other number? Now, when you want to measure angles that are less than 1 degree, you can either use decimal or minute and second. So we will talk about that. As I said before, angle has no dimensions, but it has unit. Why is that? This is a very pressing questions. I'll address here. What does dimensionless mean? Aspect ratio is also dimensionless. Can it have unit? What is pi? Is pi 180 degree? Why is the angle theta defined as the arc length over radius and not some other quantity? We'll talk about trigonometric functions, angle versus slope. We'll talk about small angle approximation. This is a very important one. And we'll also talk about, when you see angle in an expression, is it in degree or radian? We'll talk about angle between lines and planes. We'll talk about that conceptually. We'll talk about plane angle versus solid angle, and I'll show you some applications in physics. And at the very end, I also have some examples. So, what is angle? I have the pictures of the same stick. In this case, the stick is horizontal. In this case, the stick is tilted a little bit. So, this tilt, we mark it with an arc like this. It can be here, here, or here, it doesn't matter. And we denote it with a symbol like theta, alpha, beta, or even x, y, a, or whatever symbol. Right. So, this tilt is called angle. In this case, I can say that this tilt with respect to the horizontal is 0. So the angle here is 0. All right. The concept of angle is not new though. It has been used from very old days. Here you can see the spokes of the wheel at different angles. Here the edge of the pyramid is at an angle. Airplane taking off at an angle. Angle is also used a lot in math and computer science. In this case, this edge of the mountain is at a smaller angle compared to this edge. Now, if you drive on a hilly area, you will notice that the road is zigzag like this. This is zigzag to reduce the slope or angle of the road so that it is easier to drive. If I build a road straight like this angle is going to be really steep and it will be difficult to drive. All right, now let's talk about how we can measure the angle. So in the very old days, it is in the Vedic scripture as well as in the Babylonian scripture, what they did is they divided the whole thing into 360 equal parts. And then if I wanted to measure this angle, I can find out how many parts this is out of 360. Let's say this is 30. Then this angle is 30. In more recent times, during Sir Isaac Newton's day, there was a smart mathematician called Roger Coates. What he observed is if I want to measure this angle, if I draw an arc, let me call this arc length as L and this radius as R, then the ratio L over R is a constant, meaning if I have a bigger radius, let me call it uppercase R, and then draw a bigger arc, let me call it uppercase L, right? Then this ratio, lowercase l over r, is same as uppercase L over R. Then, and as you can see, this angle should not change if I extend the radius, right? So then this is a good measure of this angle. Let me call it theta. So this is theta, right? Now to distinguish between measuring this way and this way, this was called radian and this was called degrees. The term radian was coined actually later by James Thomson. He was the brother of Lord Kelvin. But then these are the two different ways we can measure the angle. All right, now let's talk about this burning question. Why is a full circle 360 degrees and not a different number like 100? I found three reasons from the literature. The basic reason being, 360 is close to the number of days in a year, which is 365. From Babylonians' perspective, they used a base 60. Currently, we use a decimal system which has base 10. They used base 60, and 360 is a nice multiple in this base, so that's why 360. But the more practical reason is that 360 is a highly composite number, meaning it has many divisors. For example, 360 is divisible by all the numbers from 1 to 10 except 7. And similarly, 360 is also divisible by 12, 15, 18, 20, so on and so forth. It has many, many divisors. They are listed here. And now you may be thinking, okay, then why not take a number that is divisible with all the numbers from 1 to 10? If I do that, if I take the LCM of 1 to 10, this is a much bigger number. Similarly, if I take LCM of all the numbers from 1 to 15, it is even a bigger number. So we want a number which has many divisors, so that many different positions, many different angles we can represent as an integer. At the same time, we don't really want a huge number, right? So 360 seems more nicer than the bigger number. So that's why 360 was chosen. To measure an angle either in degree or radian, we can always use the decimal system. But when we are measuring in degrees, we can also use something called minute and second. So let's talk about that. In decimal, straightforward is 60.5, 18.4, so on and so forth. This is a decimal system. In terms of minute and second, as I mentioned before, Babylonians, they use a base 60, right? So what they did is they divided 1 degree into 60 equal parts, and each part was called arc minute. Sometimes the arc is not mentioned and it's simply mentioned as minutes. But this minute and second are different from the minute and second that we used for time. Unfortunately, they have the same name, but just keep that in mind. Similarly, 1 arc minute was subdivided into 60 arc seconds, or again the arc is many times dropped and is called seconds simply. And degree is oftentimes represented with this small circle on the top. Minute is represented with the single quote, and second is represented with a double quote. So then 1 degree is going to be 1 degree is 60 minutes, and each minute is 60 seconds. So 1 degree is going to be 60 times 60 is 360 seconds. So this is a kind of the conversion. All right. Now once we have that, we can easily convert between degrees and minutes, right? For example, 18.4 degree is going to be 18 degree, and 0.4 degree is 4 by 10 degree, and each degree is 60 minutes. So this is going to be in minutes. So this is going to be 18 degree and 4 times 6 is 24, 18 degree and 24 minutes, right? Similarly, 10 degree 12 seconds is going to be 10.00333 degree, right? We can do this conversion. All right, so this is one of the most burning questions students typically have, and the question is, angle has no dimensions but it has unit. Why is that? All right, so let's first make sure that we understand why it has no dimensions. So the angle is defined as arc length over radius. Now, if I take the dimension that is represented by the square bracket, so dimension of length is L, and then radius is also a length, so that is also a length. So this is L to the power 0. That means it has no dimension, right? This 0 means it has no dimension. But why does it have unit? Remember, there are two ways to measure angle. Let me go back. One is the legacy system where we use degrees, and this is actually most practical and it's still used today. At the same time, there is also a more natural way of measuring the angle. It's called radian. So this occurs naturally in math and physics, right? So they both coexist today, and we need a way to differentiate. And that is the only reason we need a unit for angle. Next, when I say something is dimensionless, what does it mean? This is slightly off topic, but I wanted to mention it here anyway because it's going to be useful in physics. So dimensionless means, let's say for angle, it is mass to the power 0, length to the power 0, time to the power 0. That's what it means to be dimensionless. Similarly, refractive index has mass to the power 0, length to the power 0, and time to the power 0. That is the definition of dimensionless. So this means this is the value that we get for theta or refractive index that is independent of the unit used for measuring the individual components, meaning whether I use meter to measure L and R or centimeter or inch, the value that I get is going to be independent of that unit, right? It's obvious, it's trivial, but something to keep in mind. Similarly, whether I use meter per second or kilometer per hour or miles per second, whatever I use to measure the velocities, as long as I use the same unit, the final value that I'm going to get is going to be independent of that unit, right? That's what it means by dimensionless. All right, so the follow-up question then is, aspect ratio is also dimensionless. Can it have unit? So what is aspect ratio? Aspect ratio is essentially the length of a rectangle over the height of a rectangle. All right. Remember, why did we need a unit for theta? Because we were using two different systems to measure, like degree and radian. Similarly, for aspect ratio, let's say so this is a simple ratio of two lengths, right? But I want to, let's say, measure it in terms of, just for the sake of example, let's say I want to measure it in terms of percentage. So let's say A is equal to 10 meter, B is equal to 5 meter. So A over B is going to be 10 over 5 is going to be 2, right? So the aspect ratio of this rectangle is 2. But let's say I want to measure it in terms of percentage, right? So this is going to be 200%, right? So this simply means the length is twice the width. Now in this case, in some sense, right, this percentage, uh, I'm using it as a symbol, but in some sense that can be a unit, right? So instead of I'm just purely using a number, I'm using a percentage. So this can be treated as a unit, right? uh, Another example is, let's say for some applications, right, I want to measure the length in meter, but within, let's say, for example, centimeter. So this will be 500 centimeters. So in this case, the aspect ratio is going to be, A is, I'm measuring this in meter, and the height is in centimeters, so 500 centimeter. So this is going to be 1 over 50 meter over centimeter. So here in this case, since I'm not using the same unit, I must retain the unit, right? So yes, aspect ratio or other non-dimensional physical quantities, in some very rare applications, they can have unit. Next, let's try to talk about this symbol. This symbol is called pi. You see this a lot in math and physics. So we will try to see what it means. Let's draw a circle with radius r. R can be 1 meter, 1 millimeter, 100 kilometer, it doesn't matter, right? When we draw this circle, then we try to find the length of this half perimeter. If we take the radius, this will go 1 time here, 2 time, 3 time, and then there will be little more. But if we zoom in here, we will see that this point is going to be 3.14159 dot 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 times r, right? So this half perimeter is going to be this number. This is the irrational number. It's a never ending decimal number times r. So this number is a special number and it's denoted by the symbol pi, right? So pi is basically just this number. Okay, then is pi is equal to 180 degree? No, pi is not 180 degree. On the other hand, let's say if I define the angle in radian, so theta is equal to L by R, and this is in radian. Now if I take half circle, this is by definition, I'm using this number as pi. So this is pi r divided by the radius is r. So this is simply pi, but this is in radian. Now if I measure this in degree, the whole thing, we take it as 360 degree. So the half will be 180 degree, right? So then this pi radian, that is this half circle, is 180 degree. So pi is not 180 degree. We loosely say pi is equal to 180 degree, but it's more accurate to say pi radian is 180 degree. All right, next let's try to think about this question. Why do we define theta to be L over R? So I have drawn a diagram here. L is the arc length, R is the radius, H is the perpendicular height, and B is the base. So we can come up with the different ratios, and using geometry we can prove that, once for a given theta these ratios are going to be constant, right? So why do we call this specific ratio L over R to be theta and not the other ones? Actually, it is very natural. Let me just show it here. So theta is equal to L over R. So if we use this definition of theta, then when L becomes twice, when the arc length becomes twice, we expect the angle to be twice, and we can see that it does become twice. Also, when the radius becomes half, let's say the radius becomes half, and if I keep the arc length the same, right? If r becomes r by 2, the 2 goes to the top, so we expect the angle to be twice, and it does become twice. So this is a very natural, intuitive definition of angle, right? One thing to note, sometimes students get confused, is theta L by R or R by L? So think of it like this: when the L increases, right, theta should increase, so the theta is L over R. Now, just for the sake of example, if I take the other ratio, H over B, if I make the height to be twice, right, the angle doesn't become twice. So this angle is not the same as this angle, right? So this kind of doesn't make sense, right? But these are the other ratios are very important ratios, and I'm going to talk about that here. Now, the ratio L over R, we call that angle. The other ratio H over R, for example, is a function of theta. Once theta is fixed, that ratio is fixed. We call it sine theta. Similarly, cosine theta and tangent theta. So these are trigonometric functions. We will study about this in more detail in trigonometry, but for now, I'll just give you a brief preview here. Another thing is this function here, h over b, which we call tan theta, we also call that as slope. So basically, slope is h over b. That is, we call this rise over run. How much it rises over this much run, right? So we call that as slope. Okay. Another thing to note is this angle L over R is in radian, but the other ratios, they are simply numbers. All right. Okay. Also, when the angle is small, there are some approximations we can make, and this comes actually very handy in physics. So I wanted to discuss that here. So when theta is very, very small, so this is theta. So when the theta is very small, so let's say this is theta. right? So this is going to be H, this arc length is going to be L, and this is going to be B, right? So you can see that when theta becomes very small, H and L are very close. They are the practically same, and the B, right, is same as the radius, right? So once we put these values, we will see that, sine theta is H over R, so H becomes L, so L over R is theta. So for small angles, sine theta is equal to theta. Similarly, tan theta will be equal to theta, and cosine theta will be 1. Again, so this theta, they are in radians, not in degree, they are in radians. If these are in radians, so these are simply numbers, right? All right. So in math expressions, right, theta is in radians by default. That's the natural way of defining theta, right? Um, so this has to do with this question, right? However, you know, in sometimes you will see expressions like sine pi theta over 180. So in this case, it is in degree. What happens is this. Let's say theta is in degree. You want to express theta is in degree, right? In degree. So we know that pi radian is equal to 180 degree, right? So if theta is in degree, if I want to convert it to radian, if I multiply with pi radian over 180 degree, so pi radian is equal to 180 degree. So this ratio is simply 1. So if I multiply something with 1, the value doesn't change. Now if I do this, the degree cancels out. This is simply, pi theta over 180 radian, but this theta here is in degree. This theta is in degree, right? So when you see in expression something like this, theta is in degree, but in the most expressions you will see sine theta, and the theta is in radian, right? So this is one question that I get very often. Uh, uh, is theta in degree or radian, right? So theta by default is in radian. All right. So here I have tried to show you some numerical values here. On the x-axis I have theta, on the y-axis I have plotted different plots. The red one is y is equal to theta, right? So this is again a line at 45 degree, and then this is sine theta, this is cosine theta, and this is tan theta. So as you can see, for when the angle is less than 0.35 radian or about 20 degree in this region here, right? Theta, sine theta, and tan theta, they are very close to each other, and the cosine theta is roughly 1. So this is actually 1. So you can see the actual values here. For theta, about 20 degree, the actual value is 343. We are approximating this to be theta is like 2%, 4%, and 6% error, right? So for small theta, we can make this approximation that sine theta is equal to theta, tan theta is equal to theta, and cosine theta is roughly 1. All right, angle is always defined between two lines, but we can extend that idea to define angle between a line and a plane, or a plane and a plane. Okay, so here I have one line, this is another line. The way we define angle is either I can move this line parallel and call this angle theta, or I can also extend these lines, and this will be the same angle theta. The angle between a line and a plane, so if I have a line here, I can move this parallel, this is the same line, then what I can do is draw a perpendicular on the plane, and then draw this line. So this will be the angle theta. So this will be the angle between the line and a plane. If I have two planes, if they do not if they are not parallel, they will intersect. When they intersect, let's say this is our line of intersection, then if I take another plane, take a cross section of these planes, and that plane that is doing the cross section has to be normal to this line, then what we'll see is we'll get this line, and this angle is the angle between the two planes. Uh, Usually, actually, given the equation of a line and a plane, there are formulas to calculate the angle. So I'm not going to go into the numericals here. I'm just showing you the concept. So when I say angle, it refers to a plane angle. We simply call it angle. There is another kind of angle called solid angle. Plane angle is in 2D, that is defined between two lines. So this is plane angle. Solid angle is in three-dimensional space. So they are very similar. So let me explain it in parallel. So the plane angle is defined as the arc length over radius. This is a plane angle. Similarly, instead of arc length, if I take a spherical surface, that area of that surface over the radius square, so that is defined as the solid angle. So given a spherical area, if we connect that to the center, all the lines, so that space that it occupies, that angle, that is the solid angle, and this is the definition. Just like this is dimensional less, this also you can see area has the dimension of length square, and this is also length square, that is also dimension less. Here theta is in radian, right? This is by definition. Similarly, theta here we call it solid angle in steradian, symbol is SR. Just like theta here is independent of the L and R, similarly the solid angle is also independent of A and R, although they are used to define it. It's independent of it. Just like whole circle is 2 pi radian or 360 degrees, the whole sphere, that is whole spherical area is surface area of a sphere is 4 pi r square, and if we divide that with the radius square, we get 4 pi. So the solid angle of the whole spherical surface is 4 pi steradian, and that is also in terms of degree equivalent, that's 360 square by pi square degree. So we can use the radian to degree for conversion. Similarly, we can use steradian to square degree for conversion. Okay, one thing I wanted to mention. So this is a ball. Like the solid angle, to define solid angle, the surface doesn't have to be a circular outline. I can draw any arbitrary shape surface here and join each point to the center of the ball, and then the angle that this surface is going to subtend at the center is given by this area divided by the radius square. I actually drew on my daughter's ball. Hopefully she doesn't yell at me. All right, we are going to hear about the angle a lot in physics. Here I have just a few of the examples when we deal with vectors or circular motion or wave motion or flux. All right, so now let's take a look at some examples. In the definition of an angle, theta is equal to L over R. For theta to be in radian, L and R must be measured in meter. So this is definitely false because theta is a non-dimensional quantity, it's length over length, and as long as they are same unit like meter over meter or inch over inch or whatever, it's fine, right? They don't have to be meters. Mark all the correct statements. Okay, there are two figures A and B. In figure A, theta is equal to L over R. Here, notice that the L is the hypotenuse, right? It's not the arc length. So here, theta is S over R, right? So not L over R. So this is definitely not correct. Theta is equal to H over R. H over R, that is definitely not correct. That is sine theta. H over R is a function of theta. Yes, that is sine theta. So that is a function of theta. For given R, if S doubles then theta doubles. Yes, if S doubles then theta doubles. So that's correct. For a given R, if H doubles then theta doubles. If H doubles then theta doesn't double, right? So that's not correct. We saw this earlier. In figure B, L1 over R1 is L2 by R2. So here the definition of theta is basically L1 over R1, or it can be L2 over R2, right? So they have to be the same, right? So this is definitely incorrect. Ratio of half perimeter to radius is approximately 3.142. Full perimeter is 2 pi r, half perimeter is pi r. Ratio of that to radius. So basically this is pi is 3.142. So G is the correct. For small angle, sin theta is equal to theta. So sin 0.1 degree is 0.1. For sin theta to be equal to theta, theta has to be in radian, right? But here it is in degree. So this is definitely false. Sin 9 this degree is how much? So 9 degree is a small angle, so we can use the approximation sin theta is equal to theta. So, but theta has to be in radian. So sin 9 degree is going to be, pi radian is 180 degree. So this is a small angle. So it's going to be 9 pi over 180. So this is 20. So this is 3.142 divided by 20. So if I divide this with 10, this is 0.3142 by 2. So this is going to be 0.16, right? So 0.16. For small angles, angle in radian and slope are the same. We know that for small angle, theta is same as sin theta is same as tan theta. So the angle in radian and the slope and tan theta, they are the same. So this is true. The restoring force on a simple pendulum is given as follows. The magnitude of the restoring force, mark all that apply. So we have not studied about the restoring force. We'll study about that in simple harmonic motion. But I still give that problem here because I don't need to know what is restoring force. All that I need is this equation. So F goes as mg sine theta. So let's take a look at the choices one at a time. It's proportional to theta. No, F is proportional to sine theta, not theta. So this is incorrect. It's proportional to x for small theta. So for small theta, right, it will be mg theta. So sine theta is equal to theta for small theta. And theta is going to be arc length over radius. So this is going to be mg, theta is going to be x over L. Alright. So it's proportional to x for small theta. Yes, so for small theta it is proportional, F is proportional to x. This is correct. It's proportional to L for small theta. No, it is inversely proportional to L. Increases linearly with increasing x for small x. So for small x, when x is going to be small, theta is going to be small. So this expression will be valid. So yes, F increases linearly with x for small x. So this is also correct. Is undefined at theta is equal to 0. At theta is equal to 0, sine theta is 0. So F is very well defined. So again, E is incorrect. For small angle, sine theta is linear in theta. So sine theta is equal to theta. Similarly, cosine theta, we need to find an expression for cosine theta in terms of theta. So somehow if we can relate cosine theta to sine theta, we are good. So there are actually a few ways we can do it. So let me show you. First, I know that sine square theta plus cosine square theta is equal to 1. This is an identity. So this tells me cosine theta is going to be 1 minus sine square theta, square root of that. And for small angles, sine square theta is basically theta square. So it's 1 minus theta square and a square root of that. So I'm going to use the binomial approximation 1 plus x to the power n to 1 plus nx. That is for small x. So if I use that, this is going to be 1 minus theta square by 2. Right? Another way I can do it is I can use the cosine 2 theta expression. So cosine theta is same as cosine 2 times theta by 2. This is the same thing, right? So this is, if I use this as theta, so this is cosine 2 theta is 1 minus 2 sine square theta. Here is theta by 2. So this is again 1 minus 2 sine square. Since theta is small, this is going to be theta by 2 square. Theta by 2 square. So again, this gives me 1 minus theta square by 2. Another way I can do it is use the Taylor series for cosine theta. So cosine theta in terms of the Taylor series is 1 minus theta square by 2 factorial plus theta 4 by 4 factorial minus theta 6 factorial plus so on and so forth. So for small theta, we can neglect this higher order term, so that leaves me with 1 minus theta square by 2 factorial is just 2. Theta square over 2, right? So cosine theta is quadratic in theta, and this is the correct expression. So C is the correct choice. All right. Here actually I'm showing yet another way. So cosine theta is cosine 2 theta by 2. Now I'm using the formula cosine 2 theta is cosine square theta minus sine square theta. So if I do that, I get cosine square theta by 2 minus sine square theta by 2. And then for small theta, I'm using the approximation cosine theta is equal to 1 and sine theta is equal to theta. So this becomes 1 and this becomes, theta by 2 square. And then I get this. But this is not the same as this, right? I should get 1 minus theta square by 2. Here I'm getting 1 minus theta square by 4. So I have made a mistake. Try to pause the video and figure out where I made a mistake. Alright. Mistake is here. So cosine square theta by 2 is close to 1. How close? So cosine square theta by 2, right? This is going to be 1 minus sine square theta by 2. So this is an identity. So there is no approximation involved there. Now I can use a small angle approximation. This is going to be 1 minus theta by 2 square, right? So this is close to 1 but not exactly 1. And how close? This close, right? So instead of 1, if I use 1 minus theta by 2 square here, then I'll get the right result. And the reason I cannot neglect this second order term, because I am actually keeping the second order term, so I cannot neglect this here. If cosine theta is 0.9, theta is approximately. If you remember this formula, you can of course use this, but if not, it's not very difficult to derive. So I know sine square theta plus cos square theta is equal to 1. So for small theta, this is going to be theta square. Cosine square theta is basically 0.9 square. And since cosine theta is very close to 1, that's why I'm able to use a small angle approximation. This is going to be 1, so this gives me theta square is equal to, 1 minus 0.9 square is basically 0.81. So the theta, so this is approximately 0.2, right? So square root of 2, right? A is the correct choice. Wave equation is given as follows, where lambda is the wavelength, t is the time period, and phi naught is the initial phase. The argument of sine function. So basically, this is the argument. So that is also called the phase. Alright, so that's given as follows. What will be the phase at x is equal to this, t is equal to this, and phi is equal to 90 degrees. Alright, so the phase is basically 2 pi by lambda, and x is given lambda by 2, and then minus 2 pi over t, and then small time is given as capital time, plus phi naught. So this lambda cancels, this 2 cancels, so this is going to be pi minus, this t cancels, minus 2 pi plus phi naught. So this is going to be minus pi plus phi naught. Okay, what is phi naught? Phi naught is 90 degrees. So this is where the catch is there, right? So I cannot just write 90 here, right? Whenever you see the pi's, right, Thetas are in radians, right? So I have to convert this to radians. So 90 degree is pi over 2. So this is pi over 2. So then minus pi plus pi over 2 is minus pi by 2, right? So then A will be the correct choice. You can get tricked here if you just put 90. So this will be 90 minus pi, and you'll think that this is the correct choice, but this is not the correct choice. What is the solid angle subtended at one corner of a cuboid? So at the one corner, the entire space is shared by 8 cuboids, as you can see in this picture. So the entire space is 4 pi steradian, which is shared by 8 cuboids. So this is going to be pi over 2 steradian. Derive the solid angle for a cone with half angle theta, as shown in this picture, and then we need to verify the result for these angles. So cone is a part of a sphere. So let me try to draw the sphere. So this is the radius of the sphere. So this is going to be a sphere like this. Okay, and then what I'll do is at some angle phi, right, I try to make a small strip. This is at angle phi, and a slightly larger angle, so phi plus d phi. I take this strip here. Okay, now I try to take this surface area over the radius square. So my small solid angle, let me call it d omega, is going to be, so this is going to be ds over r square. So what will be the area of this? So area of this is going to be, so this is a circular, right? If I cut it and open it, the small strip is going to have length that is 2 pi and this radius. So 2 pi, what is going to be this radius? This radius is going to be r sine theta, right? R sine phi in this case. And what is going to be the height? That height is going to be this small arc here, and that is going to be, r d phi, right? R d phi. That is my small angle here. So that is going to be, ds is going to be this times this. So that is going to be 2 pi r sine phi r d phi. So this is the surface area, that area divided by r square, right? So that is the formula of the solid angle. So again, this cancels. So this, and then if I integrate, that gives me omega is integral of 2 pi sine phi d phi, and the phi goes from 0 to theta. 0 to theta, right? So this will be 2 pi, sine theta is minus cosine phi, and the limit is from 0 to theta. So this gives me cosine 0 will be 1, and then this is cosine theta. So that is going to be 1 minus cosine theta, right? So 2 pi 1 minus cosine theta, right? So this is going to be my solid angle omega. Okay, so that is the formula. So let's check at theta is equal to 0. If theta is equal to 0, cosine theta is 1, so 1 minus 1 is 0. So omega is equal to 0. That makes sense. If theta is 0, right? It's just basically a line. There is no solid angle. If theta is equal to pi by 2, so that is pi by 2 is basically half the sphere. So if it's pi by 2, then this is 0. 1 minus 0 is just 1. So it's basically omega is 2 pi. That also makes sense because the entire space is 4 pi. So half the sphere will be 2 pi. And then if theta is equal to pi. So that is basically entire space. Cosine pi is -1, so -1 and then negative is +1. So this is going to be 2. So this is 4 pi. Omega is equal to 4 pi. So the entire space, entire solid angle at a point is 4 pi. So it all makes sense, right? So this is the formula. That concludes all the examples I had. But before ending, I wanted to say one thing. So the problems that we solved are actually very simple. You are not going to be asked those straight. That will be part of a bigger problem. Like this example from JEE Advanced 2025. Here it is given theta naught as cosine inverse 0.9. From there, we actually find out the value of theta naught, so on and so forth, right? So, the things that we learn are going to be useful as part in solving, bigger problems. All right. That is it for this video. If there is any feedback, please let me know. I'll see you in the next video.